So, hello everyone, and welcome to my presentation of my final master thesis. First of all, let me introduce myself briefly. My name is Daniel Martinez Capilla. I was born in a small town which is at 40 minutes from here. And I did my bachelor's degree at the University of Girona, and then I had the great chance to join the Vibot program. And as Robert was introducing in the presentation from before, we have 4 semesters, where the first semester we are going to different universities. And in the last semester we should go and we should pick a host university to do our final thesis. And I went to the University of Tennessee in the States, to the Department of Electrical Engineering and Computer Science. And I was working on that project, which I called as Sign Language Translator using Microsoft Kinect Xbox 360, with the supervision of Hairong and Meriaudeau. So this is the outline of my presentation. We are going to start with the introduction, where I will explain you the problem, and which is my thesis proposal. Then on the second section, the methodology, I give the details of all the sections and all the parts of the project. On the third section, I'm going to evaluate the results, and I'm going to tell you about the accuracy of the system. And finally, we will end up the presentation with the conclusions. So let's start by the problem definition. Humans have been endowed by nature with a voice capability. When we are kids, our parents show us the way that we have to communicate with others. This is the spoken language. But unfortunately, not everybody possesses this capability. I'm talking about deaf people that they are not so lucky that we are, and they cannot communicate in the same way that we do. To solve that problem, several dictionaries of signs have been defined, but this dictionary of signs contain something else than just signs. Okay, there are other components that play also a role. And especially this kind of sign language, they are quite hard to learn because it's not easy. It's not easy at all. And let's say, for example, how many of you know sign language from here? Raise your hand. No? Okay. So as you can have an idea. So the proposal of the project at the beginning was to build a system so that an ordinary user will be in front of a computer, and a deaf user will be in front of a camera, like executing some signs. And the system must be able to translate these signs to the corresponding word in the spoken language. Okay? But some considerations must be taken into account here. The first thing, as I told you, sign language, they also combine other things than just signs. Also the morphology, the syntax play an important role, meaning that if we execute the signs in different order, the meaning can totally change. Also the movements of facial expressions that are quite hard to track also are important to discern between different signs. So I set up a feasible goal at the beginning by defining this list of 14 words that transmit the need of the user. Okay? By combining these words, I also define a list of sentences that can let the communication between people. One of the goals was to design an interactive, easy-to-use user interface so that the user won't have the need to learn the first time that he faces the application. So all the options are quite logic. The system must work on real time, given an input sign. We want to know the corresponding word just right after the sign is executed. Also, I want to let the user add new words to the dictionary, as you will see at the end of the application. This is working. And here, some people have been working on that before. I mean, it's an open research area, but I must say that nowadays there is no sign language translator that is working for a whole dictionary of signs and perfectly working. And they mostly use hidden Markov model and neural networks classifiers. Okay? So the proposal here was to use the advantage of the Kinect to get the sign description. And I introduced an 8-dimensional descriptor and an efficient needless network based on dynamic time graphing algorithm to solve the same problem. Okay? So for the setup, I'm using the Microsoft Kinect Xbox 360 camera. This camera is called as RGB camera because for every single pixel of the field of view, it provides the information about color, RGB, and also the information in depth. Okay, because for every pixel, we know how far this pixel is with respect to the origin of the camera. The driver that I'm using is the OpenAI. There are several open source code, but this one maybe was the one that provided me the most suitable functionalities that I had to use for the project. So let's jump to the methodology now. I'm going to start with a diagram of blocks. This diagram of blocks, the first thing that I want to say you is that, okay, it's not clear, but here it says test gesture, and here it says gesture dictionary. When I'm talking about test gesture, is the gesture that I'm going to match with the, I mean, when the diff user is executing a gesture, this is considered the test gesture. And in the gesture dictionary, we have all the samples that we record. Okay, so all the signs that are in the dictionary are recorded here. All the samples from the dictionary are here. These diagram of blocks are all the functionalities that the system executes every time that we get a new frame from the camera. So once we get that frame, we display that frame in the screen, and we overlap the skeleton of the user. You will see at the end in the demo. At that point, we need to check if we are recording. When we are recording, I mean if we want to test or we want to train or add a new word. Okay? If we are not recording, we just get a new frame and we do the same. But at the point that we want to record, there are three main functions that are executed. The first one is to obtain the joints of interest. The second one, to normalize the data. The third one, to build the frame descriptor. At that point, we check which is the working mode. If we are testing or we are training. If we are training, meaning that we are adding a new word to the dictionary, we just add this frame descriptor, okay, just the descriptor for the frame, we add it to the corresponding sign in the dictionary. This is easy. I mean, if we are, let's say for example, we are adding the word room to the dictionary, so every frame of the word of the sign room will be added to the corresponding sign room in the dictionary. Okay? And then we get a new frame. If we are testing, we add the frame descriptor to the test sample. And in that case, if we are testing, we should check which is the last frame of the sign. Because at the point that we reach the last frame, which I define it as when we have the hands lower than the hip, than the position of the hip for a consecutive number of frames, at that point, we will compare the test sample, because it's finished, with the dictionary by using a classifier. And the output of this classifier will be the corresponding word in the spoken language. Okay? So, joints of interest. By using OpenAI, which is the driver that I mentioned before, we can track up to 15 different joints of interest. But in that project, only 6 out of these 15 joints are used, where we have 6 joints, which are both elbows and both hands, that these joints are used for the description of the sign. And then we have 2 different joints, the head and the torso joint, which is the middle one, that these are used for normalization purposes. So how do we normalize the data? I want to make the system robust to invariant to both pose and size of the user. So the first normalization is in position. Here we have this example. You can easily understand the idea. We have the same user, but the user can be at different positions of the room. As you can see, the same user, depending if it's on the front of the room or if it's on the back of the room, it can has, I mean, the distance from one joint to another one are totally different. And this should be taken into account. So to solve that problem, the idea that I proposed was to normalize all the joints with respect to the torso position by using spherical coordinates. If we have the hand at that point, so instead of using X, Y, and Z of that joint, I will use the spherical coordinates radius, which is the vector that is defined from the torso to the joint of the hand, and also the 2 angles that defines this vector. Okay? I'm calling here the radius D instead of R, sorry. And the angles I'm calling theta and phi. These are the formulas, but I'm not going to get into details because it's just a pure transformation. So the second normalization in size, we have that family. In this family, we should consider that the training samples, meaning the samples that are in the dictionary, they belong all to the same user, which in that case is myself. So the system must work no matter the size of the user is. In that case, we have the father in that case that is bigger than the son, so it should work for both of them. To solve that problem, taking the advantage that we are working with spherical coordinates, the idea here is to use this distance, which is defined from the joint head to the dorsal joint, as normalization factor. Okay? So we will divide all the distance, all the radius from the joints by this normalization factor dHt. And by doing so, we'll solve the normalization in size. Okay, once we reach that point, we should describe the data that we have. At the beginning, I tried to build a 12-dimensional descriptor because we have 4 joints and 3 different coordinates for all the joints. But I realized after evaluating the results that only 2 out of these 3 coordinates were meaningful. Okay, theta, you will see at the end in the evaluation and results section, theta is not meaningful. So that's why we just don't care about the theta, and we will take into account only d and phi. Okay, which ends up with an 8-dimensional descriptor. So for the classifier, here I developed 2 different classifiers, which both are based in nearest neighbor by using the dynamic time warping algorithm as a cost function. So since both of them are using this algorithm, the first thing that I'm going to show you is the main idea of that algorithm, okay? So dynamic time warping algorithm tells about the similarity between 2 sequences that they differ in length. I hope you will properly see the letters here, but we have here, it's easy to understand that this algorithm by having a look to that example. We have the word cat here, and we have the word hello, and the word bad, sorry. And we want to know if the word cat is closer to hello or closer to bad. So by running this algorithm, sorry, every letter here we assign the value. I mean here 8, here E has the value of 5 because it's the corresponding ordinal number in the alphabet, being A1, B2, and so on. So if we assign this number to every letter and we run the algorithm, we get a similarity coefficient of 30. Okay, which is telling about the similarity between cat and hello. We can say that the word cat and bad are more similar than the word cat and hello. Okay. In the case of our system, instead of having just a letter here, what we will have here is the 8-dimensional descriptor that I told you before. So the first classifier that I developed here was a nearest neighbor, where for every sample from the training set, we compute this similarity coefficient by using the dynamic time warping algorithm, and we get all the similarity coefficients for all the training samples. And from these samples, we have a look to we search which is the smallest one, which in that case is that one, 25. And since this 25 belongs to the sign doctor, we assign the test sample as the word design doctor. Okay. For the second modification of this classifier, I call it nearest group, because instead of nearest neighbor, we are matching with the group that has the smallest mean dynamic time warping similarity coefficient. In that case, as you can see here, we are computing the mean for all the similarities in the same group, and we are matching the test sample with the class that has the smallest value. In that case, it's doctor, and that's why the test sample is matched with the class doctor. So let's jump now to the evaluation and results. In order to test our system, to evaluate our system, I defined a total of 70 training samples, which means that I have 14 words in the dictionary, and for every sign from the dictionary, I executed 5 different samples. Okay, so 5 by 14, 30. And then for the test samples, for the test set, I asked 4 of my colleagues to run 3 times the same sign. So we have 14 by 3 samples. This ends up with 168 test samples. Okay. Here you cannot see it properly, I guess, but this is myself, and all the training samples are also from myself. But in that case, as you can see, the position is totally different. So all the samples are taken in different positions of the room, the ones that belongs to myself, so that we can test also the normalization in position. Okay? Well, so here we have 3 different approaches. This is the Cartesian, and these 2 are the spherical ones. Here I want to mention the improvement that we have once we normalize the data in size. Okay, once we apply the normalization in size. Here we can see that because the Cartesian, you should consider that the Cartesian approach is not taking into account the normalization in size. It's only considering the normalization in position. And both the sphericals, they are taking into account the normalization in size. The highest accuracy that we have here is about 85%, which is in that case. And here, in the case of the spherical one, where we are considering the normalization in size, the highest one is 95%, which the difference is quite big enough to that. And this, I mean, with that we can say that the normalization in position, sorry, in size is working properly and it's quite useful. The next thing, I'm applying a different weight to the joint that we are using. We have both hands and we have both elbows. When executing a sign, the hand is moving more than the elbow, which means that the information provided by the hand is more meaningful than the information provided by the elbow. So here, after testing the system for all the configurations, I realized that the best configuration is when we apply an 80% of weight to the hands and 20% of weight to the elbows. Okay? Another one of the combinations for the configuration was the features that we are using. As I told you at the beginning, we have the values, sorry, the coordinates d, phi, and theta. And for the best configuration, we are only using d and phi. Here, this one from here belongs to the value of theta. As you can see, the accuracy is 4, 7, 8, 5, 8, which is always lower than 10. Okay? We can easily understand this by looking to that graph. Here we have, this is the values of d, this is the values of theta, and this is the value of phi. So after evaluating and plotting all the information for all the graphs and for all the signs, and having a look to the behavior of the different coordinates along the frames for every sign, I realized that the value of theta remains almost the same, has almost the same behavior for all the signs. So that's why it's not meaningful, and that's why if we try to use only theta, the accuracy that we get is lower. I mean, it's nothing. Okay. So here the best configuration is when we use the values of the radius d and the angle phi, and we reach an accuracy of 95.23. And here, the last table, here I'm plotting the information and the accuracies for every one of the signs. We have different configurations, and as you can see, for all the words, the system is properly working. I mean, we get almost an accuracy of 100%. For all the 12 samples that we have for every sign are rightly classified. But we have a conflicting word here, hungry, because the accuracy is not good at all. This is because this sign is where it is distributed here near the torso, something like this. With the right hand, we should do something like this. And since considering the characteristics that I'm using, which are the angles, phi, theta, and the radius d, here a slight variation on the movement. Sorry, all the joints, as you know, are described with respect to the torso. So here a slight variation with respect to the torso will change a lot the value of the angle. Okay, if we have here the hand, the angle here will be, for example, 0, and if we move here, the angle will be 180. Okay, so that's why this work is conflictive, and in order to solve that problem, we will need to use other features. So now let me show you a demo. First of all, in that demo, I'm showing you the setup. We have the camera, we have the computer, and we have the user. A calibration position is required, okay? And here I'm showing you how all the test samples are executed. So we have the user executing the signs, and the corresponding output is shown here in the output display. The velocity is 3 times faster, so. And here the next step will be to add a new sign. I want to add the sign toilet, which is not in the dictionary. If you see, I tried to run to execute it first, and the output is not the right one. This is because it's not in the dictionary. So if we input a new sign, toilet, and the username, Danny in that case, and we train it, now at that point the sign is already in the dictionary, we can test it, and the output is the right one. If we move to other positions of the room, the output is still in the right one. Okay? And the last thing here, I'm going to show you how to build the sentences by combining different basic words. So in that case, if I say, I am sick, we get I am sick. And in that case, if we say, I want doctor, we will get the output, I want to see a doctor. Okay? This is somehow the way that sign language works, because they are not speaking in the same way that we do. They are avoiding some verbs, some subjects and some things that, I mean, they are not speaking in the same way that we do. Okay? They are speaking somehow like Hindi. Okay. So in the presentation, I'm going to talk about the conclusions. Well, I can see that the system is working since the best accuracy that we reach is up to 95.23%. From the 168 test samples that I have, only 8 are misclassified, where 6 out of these 8 misclassified samples belong to the same conflict before handling. Okay? The initial goal was satisfied because we wanted to prove efficiency, to show the efficiency of the Microsoft Kinect by the combination of a descriptor, the descriptor that I introduced here, the dimensional descriptor, and 2 different classifiers, okay, without sacrificing the accuracy. As I told you, there are other people that are working on different projects, like this one, on similar projects, and the accuracy, if we take into account the signs that we are using, the accuracy is pretty much the same. So with a combination of 14 basic signs, we can define a total of 12 basic sentences that can allow the communication. I can say, I want to go to the doctor, or I need to go to the toilet. I mean, you can check the sentences on my master thesis report. And here, one of the features will be to, I mean, because right now the system is working, but all the signs are homemade. Okay? It's working. We took into account the characteristics that the Kinect provides us and the features that we get from the Kinect, and we defined our own sign language. Okay? So I would like to make this system working with a more official sign language, but in that case I will need to consider all the characteristics, all the components that I mentioned at the beginning. We'll need to consider, for example, finger positions, facial expressions, lip movement, which is not easy, and it will take time, but I think it can be possible to do it one day, okay? Because there is a lot of people that is working on that project. Also, another way to improve that system will be to define a new way to recognize the initial point of a sign. Right now, I'm considering that the starting point of an execution of a sign is when we join the hands lower than the tip for a consecutive number of joints. So this can be improved as well. And also, another thing will be to reduce the number of dimensions by using appreciate, for example, when describing the sign. Okay? So that's everything. Well, you can find further information in my personal web page where all the project is described, and you can find the report, the paper, and the poster. So now it's your turn. If you have any questions, please feel free to ask.
You can ask questions if you want. I explain all things. Any questions? Don't be shy. There's some place in here, so there's no need to be standing up. Don't be scared, you don't mind.
Normalize in time. Let's say there's people executing the gesture faster than others.
So the advantage of using this dynamic time graphing algorithm that I mentioned here is because we can compare different sequences that differ in length. When I say length, in our case, is, as you say, is the frame length, which means the duration of the execution of the sign. Here, I mean, this example, I think it's more clear. We have the word hello, and we are comparing with a word that is 3 letters over one that is 5 letters. So, I mean, it's at that point that we are considering the difference in length. You can compare the same sign with, I don't know, maybe 100 frames, and if another user executes the same sign, obviously it's not going to be the same number of frames. So you can use this algorithm to compare a frame of 100 with one of 2000. Obviously, if you compare one of 500 with one of 100, it's not going to match the right output. But this is the algorithm that allows to deal with the duration of the sign.
Any more questions? No? Sorry.
Hello.
I think so, yeah.
You said that you had problems recognizing that sign because there was a problem with the angles. It said it recognized 0 as 180. There was just a discontinuity in the feature space. So you said that to improve that, you would consider adding new features, but could you get the same effect by just changing the distance metric so that 0 and 180 in terms of angles became closer? Have you considered that, or is that incompatible with the time warping?
This is something that is explained on the report, because right now I'm considering something like you say. As you know, when we have a circle, we have 360 degrees, and the joint can be displayed in the position, let's say, for example, the angle 10, and one can be in the angle 350. The difference between those angles, I cannot directly subtract, because otherwise it would be like 340, right? So at that point, I'm using this adaptation in angle, because the distance is the closest one. It's not 340, but it is 20, right? From 110 to 350. But the idea that you say, I mean, I don't get the point of using this adaptation. Where do you want to apply that? You mean we have this conflicting word because the angles, if we are taking into account that the joint is here in the middle, if we are in the left side of the joint, we'll have like a component, an angle, which will be 0, and if we are in the right side, it will be 180. So the data is totally different.
But logically, it's the same. It's a posture that's very similar.
Yeah, I got you now.
It's just a problem that you see reoccurring when you use spherical coordinates, and there's normally simplistic ways to solve that problem.
Yeah, you are right. Yeah, it will be interesting to try this adaptation. Yeah.
I've got one last question. How does it scale? Have you tried to stretch your system and add more and more signs? And at what point do you get to a number of signs where you start to get a lot of confusion between the signs?
Well, here the main constraint is that, well, that's why I defined my home-made dictionary, because it allows you, I mean, all the signs that were near the torso, they were misclassified. So considering the signs that I only have right now in the dictionary, there is only one sign that can be conflicted. At the point that you are executing the signs like in other positions, since they are quite different between them, the system is working. I try to use, now I have 14 different signs, and I work with maybe 4 more signs, but it was just to find the conflictive signs. When I get the point where all the signs that are executed in the torso were conflictive, I just kept one of them. But yeah, maybe I tried 4 more signs, but no. At the point that, if you consider the characteristics that we are using, you should take this into account when defining a new sign for this system. So that's why it will be interesting to improve it and use other kind of features.
Thanks.
Questions? We move to the next talk. Thank you. Now we have Patricia